In this nugget, we're going to take a look at taking your address space and breaking it up so that you can address smaller subnetworks. We'll also look at going in the opposite direction. We'll see how we can summarize a whole bunch of addresses into one SuperNet type of address. Now, before we do absolutely anything, we're going to build our handy dandy conversion chart. That's what you would do if you walked into an exam environment for this particular certification. You would grab the scratch paper right away and you would do this. 2 raised to the 7, to the 6, to the 5, to the 4, to the 3, to the 2, to the 1, and to the 0. You're doing this right away because you know you're going to need it in this particular exam. And then underneath these exponential representations, we put the value. So this is 1, 2, 4, 8, 16, 32, 64, 128. I, of course, originally taught you about this where we were converting from binary to decimal and decimal to binary. Okay, great. We're going to use this chart in this nugget a lot, as you might guess. But let's back up for a moment. Why do we subnet? Why is this something that we would do? Well, look at this. Let's say we want to use inside our network the popular private use only 10.x, as we like to refer to it, address space. There is this handy formula that you can utilize here for how many hosts this addressing scheme would accommodate. We know that the host identification portion of this address is 24 bits. And we know this by looking at the mask. It's 255.0.0.0. This 255, all these bits being turned on, indicates that that's the network portion of the address. Here is the host portion of the address. The formula for how many hosts we can accommodate is 2 raised to the number of host bits minus 2. This is going to equal the number of hosts that we can accommodate. In our example here, we would need a scientific calculator in order to solve it. There's so many hosts we can accommodate. In fact, let me grab one. So that would be 2x to the y 24 minus 2. Wow. So we can accommodate 16,777,214 host systems given this particular numbering scenario. Is there any time where you would want 16 million devices inside the same network portion, inside the same local area network of your environment? Of course not. We would have complete chaos even if we had like 10,000 machines sharing the same subnetwork, because we would have way too much broadcast traffic that would have to be dealt with. Most organizations like to keep their LAN segments around 500 or fewer computers. So the solution here is for us to subnet this address space. So what if we did this? What if we extended the mask to 255.255.255.0? Now what we're doing is we are giving ourselves the ability to create a whole bunch of subnetworks, like for instance 10.1.10/24, and we are accommodating some number of hosts. How many hosts are we accommodating? Well, 2 to the h minus 2. In this case, it's going to be 8 host bits, so it's 2 raised to the 8 minus 2. And we can kind of tell what 2 to the 8 is. It would be double this number. 128 plus 128 would give us 256. So we could have 254 hosts per network given this scenario. And boy, that sounds great to me. Let's say that works perfectly for our design. By the way, if we take and extend the mask like this, how many additional networks can we create? Well, you can always answer that question with an even simpler formula. It's 2 raised to the n, where n is your network bits. Yeah. So here we're extending the network bit portion by 16 bits, aren't we? So it would be 2 raised to the 16 is the number of subnets that we could create given this new scheme that we have devised. Let me grab our scientific calculator once again. Let's clear that calculator and we'll do 2x to the y 16 equals, we could have 65,000 and change, we don't have to be exact here, networks. And each of those networks could accommodate 254 machines. So you see the incredible power of subnetting. It's going to extend the network portion of our IP address so that we can create additional networks. And of course, this comes at the sacrifice of the number of hosts that are going to be available per network. But we don't want a lot of hosts in each network segment by design anyways. And by the way, one question that you might have is, in the hosts formula, why are we doing the -2? I mean, we don't do that when we're calculating the number of subnets given the bits that we've borrowed. The answer is, one of those minuses is for the all zeros host ID, and the other one is for the all ones. These are reserved for special purposes. The all ones in the host bits is reserved for what's called a subnet broadcasts, and the hosts all zeros situation is reserved to define that particular network itself. So there's special purposes to those two scenarios, and that's why we have the -2. So in your exam environment, you're going to just absolutely crave all of these math questions because they're going to be solved easily and you're absolutely positive of your response. There's no gray area. Let's take an example here. So let's say they tell you that you are using a /16 and you want to go ahead and subnet your /16 so that you can accommodate 30 additional subnets, and each of those subnets really needs to accommodate, let's say 100 hosts. So you look at this and you remember that 2 raised to the n equals your subnets, and you look at your conversion chart and you realize, aha, if we do 5, if we extend the mask 5 bits, we could create 32 subnets. That meets the requirement of that we need at least 30 subnets. So now you add 5 to your 16, and you know the mask that you're now going to utilize is going to be a /21. Now, we need to do a sanity check on the number of hosts that you're going to have on each of those networks. If you're using 21 bits for the network portion, that leaves 32 minus 21, that leaves 11 bits for hosts. Well, guess what? 2 raised to 11 minus 2, we don't even need to solve it. It's going to be way more than 100 hosts per subnet, so our /21 is our solution. There's no doubt in your mind about it because this is just simple math. Now, you ready to see something really cool? This chart leads us to be able to tell you just about everything about your numbering scheme. Watch this. Let's say we look at our local system and we see 192.168.0.100, and there is a /27 mask in use. By the way, what would that mask be if we wrote it out in longhand? It would be 255, that's the 8 bits, 255, another 8 bits, 255, another 8 bits, and then it would be 3 bits beyond 24 bits. So it would be these 3 bits right here. It would be 128 plus 64 plus 32. That's 12, 14, carry the 1. That is a 9, 12, 224. So that's what the /27 would look like in longhand, if you will. So given this numbering, and by the way, this is very realistic for you to see because we know 192.168.0 whatever is a common numbering scheme for a small home network situation. But watch this. With this information, we can discover just about everything about your subnetwork you would want to know. Notice the default mask is the 24 bits. We're going 3 bits into that last octet for the subnetting. So it's 1, 2, 3 deep we're going in. This number 32 becomes our magic number, if you will, and this is how the subnets are numbered. So we have 192.168.0, and then we would have 0 to 31 is one subnetwork. 192.168.0.32 to, what's 32 more? It would be 63 is the next subnet. 192.168.0.64 is the next one. It goes up to 95. 192.168.0.96 all the way up to 127. See how the subnets increment on that magic number of 32 from us going 3 bits deep into that particular segment? Wow! And by the way, this is the one we live on. 192.168.0.100 lives in this numbering scheme. Now, we can't use the first number. It's reserved. This is called the network identifier. So the network identifier is 192.168.0.96. That's the network we live on. The first usable host address on that is just one more at 97. The 127 is the broadcast for that particular subnet. So there's your broadcast. So these are those 2 unusable IP addresses that are the -2 in our formula. And we see that the 97 is the first usable, and the last usable would be a .126, wouldn't it? So 192.168.0.126. So we can number from here to here. This is not usable, this is not usable, and these are the usable addresses of which we got in our example the .100. Pretty cool, and I'm sure you want me to do another one of these, and I will. But look at all that information. So in the exam environment, you could get this right here. And they could ask you, what is your network address? Or what is your broadcast address? Or what is the first usable? What is the last usable? And you can easily calculate this on your scratch paper. And here's more good news. When you're practicing, you can check your work against a subnet calculator. Here's one I like. It's subnet-calculator.com. So I put in the address they gave me. I put in the mask bits they gave me. Here's my host address range. Here's my subnet ID. Here's my broadcast. And that is accurate to everything we just figured out by hand on paper. All right, so let's figure out everything for one more of these. Ready? 10... Whoops, let me grab a pen that works. There we go. 10.10.150.1 is our address. Again, very realistic because this is a private address. 10.10.150.1, and we notice we have a /19 mask. We want to know our network address. We want to know our broadcast address. What's the first usable on our segment? What's the last usable on our segment? Well, think about it. We've got 8 bits there representing the network. We've got another 8 bits for 16 bits. So 1010 is the network portion. And now we have our 16 bits plus our 3 bits to get 19. So we go 3 bits in once again. In this example, we go 3 bits in this particular octet to get our mask of 19. 3 bits deep goes to right here. Our magic number is 32 once again. So this time it's 10, 10, and our increments would be on 32 in this octet. So we'd have 0 and 32 and 64 and 96 and 128. Bingo! That's the one we're on here, isn't it? Because if we go 32 more, we would have, let me see, I can do that in my head. It's 160. So the next one begins at 160. So 150 is between 128 and 160. So the subnet we live on is here. That's 10.10.128.0/19. That's where we live. That's our subnet, baby. Now, what would the broadcast be? Well, the broadcast would be 10.10. We go up to as close as we can to 160, right? It would be 159.255. And now we can easily see our first usable and last usable. The first usable would be 10.10.128.1. The last usable would be 10.10.159.254. So, utilizing this cool magic number, we can figure out exactly where we're at in our network address space, and we can figure out the relevant numbers for that. Remember, when practicing, use an online site to verify your work. And here we can see the verification of everything we just arrived at in our example. Now let's take a look at something that's super easy for you to do. Not that any of this has been that difficult, but let's talk about what Juniper meant here with supernetting. Really, more accurately, they're talking about summarization or aggregation of our addresses. Supernetting is the nice kind of way to refer to it, because what we're doing is we're going the other direction with our mask. We are moving to the left with the mask to represent more networks. Let's take a look at an example. Let's say we have 192.168.10.0/24. In our routing table, we have 192.168.11.0/24, and finally 192.168.12.0/24. Can we represent these three networks in a aggregated or supernetted fashion? And the answer is yes. Let's go ahead and scrutinize this field right here from a binary perspective. It would be 0, 0, 0, let's see, 0, 1, 0, 1, 0. That gives us 10, of course, right? We have the 8 and the 2 bits turned on. Then 11, 0, 0, 0, 0, 1, 0, 1, 1, of course. And then 12, 0, 0, 0, 0, 1, 1, 0, 0. Okay, we look at this binary for that field and we see if we can mask off any bits that are in common. And of course we can. Those first 5 bits are in common. The variation comes in the last 3 bits. So we can represent all of this with 192.168.8.0/ what is our mask? Well, we've got 8 bits here, 8 bits here, and with our new mask, we've got 1, 2, 3, 4 bits here. So that is 8 plus 8 is 16, plus 4 is, oh, it's 5 bits. Woo! Careful. So 1, 2, 3, 4, 5 bits. 8 plus 8 is 16, plus 5 /21. So we see 192.168.8 8.0/21 can easily represent these three networks. Now look, everybody's different when it comes to math and particularly this subject. Some people are like, oh my gosh, this is so simple, I get it. Others are like, what is going on? I'm never going to get this. If you want additional help with this, first of all, practice makes perfect. So my flashcards are going to be hugely important for you here. But head up to the CBT Nuggets website, do a search on subnetting. You're going to see we teach this a bunch here, obviously, but there is a course dedicated just to this topic by Keith Barker. 16 nuggets just on subnetting. So if you need extra help, CBT Nuggets to the rescue. In this nugget, we examine the beautiful math behind IPv4 subnetting and supernetting. Remember, can't emphasize it enough, practice, practice, practice is what is required here. You'll learn to love it and you'll crave certification questions on this topic because there is no gray area when it comes to mathematics. I sure hope you found this nugget informative, and I'd like to thank you for viewing.